we are now looking at operational space trajectories, and so what happens here is so we were looking at joint interpolations, that if I know that a joint has to move from a initial theta value to a final theta value, or an initial position value to a final position value, what is our approach for that? So if I have one point here, one point here, if I do inverse kinematics, I will get different values at different joints. So far what we are saying is that all you do is, okay, once you have found out what the different values are, you just kind of do motion planning on each axis. Now it is not necessary that, say, if I move halfway along theta 1 direction and then halfway along theta 3 direction, so on and so forth, or halfway along all the directions, then I will actually move halfway between this point and this point. That is not guaranteed.
In fact, in most cases it won't be true, right?
Most cases it will not be true because of nonlinearity. So there is a need to program directly in the operation space, that is space in which I am operating. So there are two approaches to this. Okay, the first one is when is that I take a sequence of prescribed path points. Okay, so I am chopping it up into smaller units, and I make sure that each unit is completed at the same time. So then I am trying to ensure that by chopping up that point, I am trying to ensure that I get the path that I want, because then my variation will be within a smaller segments as I am going along the path. The other thing is that you generate a motion primitive, okay, in the operational space, a straight line, a circle, a parabola, whatever you want, and you write that primitive down in terms of a single parameter. So you parameterize the space. So if it's circle, you can describe it using a single path parameter or something. A line, you can do that. For most curves that we think of in engineering, the space is parameterizable. That means you can write it down in terms of a single variable. Now once you do that, then you simply interpolate that single variable and then everything will fall in place. So when the single variable goes halfway, the circle would have gone halfway, the line would have gone halfway, the parabola would have gone halfway, okay, and then each point on that will also correspond to something else. So there are these two approaches. Now so once you get the time sequence values in the operational space, then you have to do inverse kinematics, okay. Now when you combine this fact that you have to interpolate, you have to do inverse kinematics, that will place a limitation on your update rates, that how often can you do this process, because inverse kinematics we saw needs some inverse cos, inverse tan, or if you do Jacobian control, that is another option which is also available. Yeah.
So the first one that you're saying, interpolating a sequence of prescribed path points, that's basically a low resolution form of Jacobian control, right?
Yes, that is a low resolution form of Jacobian control. So no, it is not low resolution form of Jacobian control. What you are saying is, if I want to go from here to here, so I just give you 15 points in here. So I have to generate these 15 points anyway. Okay, I generate 15 points and give it to you. That is different from saying I want to move from here to here on a straight line. Similarly, if I want to move from here to here in a circular arc, then I can generate 15 points on this and just pass it on to you. Or I can say move from here to here on a circular arc of radius r. Okay, so if you are doing that, that is called the primitive, but if you are giving points on it, that is a sequence of points. Now, so because you are doing inverse kinematics, and it is not only inverse kinematics, you have to also pump the data out, right. So, typically you will have a computer sitting somewhere, and then from the computer you will do the inverse kinematics, and then you will pass it out to a microcontroller to implement the local motor control loop. So, there is also the data rate which you can support. So, everything combined, there is a limit to how often you can chop up the data in the operational space. So, we need to keep this in mind, that you cannot completely do the interpolation in the operation space. And so, finally, at the joint space there is always this issue of micro interpolation, which I pointed out when I was discussing the platform, right. I said there are two things: you do inverse kinematics, and then at the joint level you run a, do you remember? So, now I will go to the usual question: how many have downloaded that PPT? 1, 2, 3, 4, 5 and a half and a half. So, 5.5 people have downloaded the PPT, and obviously haven't looked at it very carefully. Okay. So, there I did talk about micro interpolation, and everybody seemed to have understood it in the class, right. So, nobody came back with questions. So, now at the joint level again, you again do joint level interpolation, okay, which is what we are talking about in the previous 3 lectures. So, that still has to be done, and the blending and things like that. Now, and this is done because if you update that, you then improve the dynamic performance of the system. Okay. So, that is why you do this linear micro interpolation at the joint level. Okay. So, and at this level the electrical people play around with all kinds of controller design issues, okay. But this one is basically the domain of the robotics people. Okay. So, here once you have done this and you pass it along, these 2 segments are done by the control people. Okay, how to update it fast, what makes it more stable, so on and so forth. So, let us look at, we will touch upon interpolating between points, then we will go away from it and we will come back to it again later. So, you have n points specifying the values of variables xc. So, xc is a vector, okay, which describe the end effector pose in the operational space, okay, x, y. So, xi at each point you have x, y, z and maybe r theta phi, whether the Euler angles or you could have something else. So, whatever it is, a vector which describes the end effector pose, that is xc, and you have n points where this is specified. So, you determine smooth interpolating vector function between the various path points. Now, what you can always do is that you take at the kth instant, you take the component ith component of it. Okay. So, if you have, so you have this vector xc that has I components. Okay. If you are just interested in position, it will be 3 x, y, z. If you are on the plane, it will only be x and y, so that will be 2. So, whichever is the number of components, you can take extricate one of those components, stack it, okay, then it becomes same as what we were discussing in the previous class, just a single dimension sequence of points. So, then you can do whatever you want, you can do cubic polynomials, linear polynomials, parabolic blends, modified trapezoids, whatever you can do it. Okay. So, I am just extricating one of the elements of it and doing a linear blend. So, though I started with that, that is obviously not a very nice thing which I finally want to implement. So, this is the more interesting one, in which we have the end effector motion which is expressed analytically, okay, straight line, curve, parabola, circle. Okay. So, we will first look at just the position, okay, we will get to orientation later. We actually know how to do the orientation also, but let us look at the position because that will explain the basics of it. So, we take a 3 into 1 vector which describes the position at any one point, and we take a continuous vector function f of sigma which is defined on a interval sigma I to sigma initial to sigma final. I mean, it is very simple, okay. And then you say, okay, fine, I just take the equation P is equal to f of sigma. So what I have done is, this field vector I have represented it as a single variable which is changing, and it gets me all three variables, sorry, and gets me a vector field. A single variable which defines a vector field P, so I can define curves in space. So this is called the parametric representation of the path tau, and we call the scalar sigma the parameter. Now when you have the values of P, this is just formal definitions. P with sigma varying in between sigma I to sigma f, it is called a path in space. Okay, so you have a vector field which is parameterized by a single variable, and then you change the variable between some parameters, between some limits, then you generate what is called a path in space. And equally important is the fact that as you increase sigma, a point P moves on the path in a particular direction, okay, and this direction is said to be a direction induced on tau by the parametric representation. So we will look at an arc representation of the path. So what we do is, first, this is a very simple definition that if P of sigma f is equal to P of sigma I, then it is a closed path, otherwise it is an open path. And if Pi is a point in open path on which a direction has been fixed, so you are specifying a direction that has been determined, you take Pi, then you define the arc length S, okay. So it is the length of the arc of the curve which ends at P and Pi if P follows Pi. So you have a Pi, right, and then P comes after that, okay. So that is the crucial thing. So you generate an arc and you say this is the length if f increases from this value to this value, and this one follows it with increasing s. So there is a sense of direction given on it also. So basically what I am telling you is the sign parameter and the formal direction, the opposite of this length if P precedes Pi. So if you take 2 points, so whether it precedes or follows depending on the value of s, that is important.
So we can say that the direction of arc is taken from sigma I to sigma f always.
In the direction sigma I to sigma f, catch is if it is a closed path, then you have a problem. So this definition is not dependent on that, because sigma I to sigma f is not defined if it is a closed path. So this just definition gets around it.
So it is defined, because if I have particular sigma I and I start increasing sigma, if I have a closed path.
So all this definition is saying is that it is linked more closely to the increasing direction rather than Pi and Pi values. So if Pi and if it is a closed path, then Pi is equal to Pf by definition.
So but the sense of direction can be made out from the velocity, from the direction of motion that we achieve by increasing sigma I.
Yes, it can be derived. So let me put it this way, it can be derived if you know that you are going around like this. Question is, if someone gives you a vector field, how do you establish that, or a parameterized vector field, you get the equations, how do you establish it? So these formal definitions help you do that, okay. And these formal definitions kind of make sure that even when you are programming more complicated paths in your program, you do not mess up. Unless you do this formally and you code this formally, you will have a problem. So it will work for simple cases, But if you have one curve like this, a circle blending with another cubic, and then going with a trapezoid, the way you make your CAD drawings, and then you want the robot to trace that path, you might land up in problem unless you do it formally and correctly. So this is already done, and pi is the origin of the arc if length of s, if length s is equal to 0. And if you take a point on the path, it corresponds to a unique value of s, and so given these properties, we can say that the arc length can be used as a parameter in a alternate parameter representation of the path tau in the form p is equal to f of s. Because I have a sense of direction, I have a sense of uniqueness, so the arc length can be used as a parameter. So all of this just to say that, okay. And so once you have this, so given a path in space, there are these three vectors which you need to define. So there is a vector which is tangent to the path, which is perhaps easy to understand, okay. Then there is n, which is called the normal unit vector. Now this is a little bit more complicated. Why? It can be infinite numbers, especially if you have a line. The tangent is very easily defined, it goes along the line, right. So which is the normal vector? You don't know, you can swing around, it can be any of these vectors can be the normal vector. But if I tell you the path is a circle, then life is easier, right, because there is a unique plane. But moment it becomes the helix, then there is a problem defining the normal vector, okay. So there is a concept of the osculating plane, right. So if it is a circle, then there is no doubt, right. Now in a helix, so what happens is you take this point P of s where you are trying to find the osculating plane, and you take two other points s plus h and s plus l, which are in the vicinity. So I have 3 points, so I can define a plane, right. I can draw a triangle through them, for example, and then what you do is you make h and l tend to 0, okay, and that will give you the oscillation plane, okay. So in theory what you do is, given the equation of the plane, you would write equation for Ps, Ps plus h, Ps plus l, okay. Given then you define the triangle, you define the normal to it in terms of these 3 points that you can do quite easily, and then you simply make L and H tend to 0. So equation for the normal will still stay. So once you have the equation for the normal, then it is defined, but that equation for the normal to the plane is not this n. This n is in the plane, is in the oscillation plane, this by definition of this, okay. So now given t and given the suppose you have now found out the osculating plane, so this n could lie either like this or like this, right. So there is two sense of directions, and n is drawn in the direction which contains the points in the vicinity of that point s, okay. So you can look it up, it is also there in Wikipedia, so amongst other things. I mean, there are lots of Wikipedia. Actually I am getting more and more impressed with it as days have gone by. I mean, 3 years ago it was not such a good thing, there were a lot of errors and things like that. Slowly they have gotten corrected to the point where I have stopped taking books out of my shelf to look at old material. Just, if it's simple like fundamental thing like oscillation, stuff like that, you can just look it up.
So what will be the case in, what will be the oscillating plane in case of straight line?
There is none, infinite number of osculating planes, so it's not always defined. So you need to have the sense of a plane. So a good homework could be to find out osculating plane in case of a helix or something, so then you have good life. So, oh, there you go. So, direction of n is so that the path tau in the neighborhood of P with respect to the plane containing T and the normal to the n lies on the same side of n. Okay, so actually the path is curving and you are trying to define some way a local circle. Okay. And this is also linked with the concept that there are 3 points in common with a circle. So, there are many concepts which are linked here. So, then the third vector is B, it is called the binormal unit vector, and finally if you write tau as function of the arc length, then these are very simple. So, then T is given by dP upon ds, okay, and n is given by d square p upon ds squared divided by the norm of that, and B is given by T cross n. So, these are very simple definitions. So, if you have those functions p as a function of s, then life is very simple. Okay, so, p is a vector function, so dP upon ds is also a vector function, d square p upon ds square is a vector function. So, you get it in this form. So, we come to rectilinear paths. So, we have a linear segment. So, this is the parameterization of it, p of s is equal to pi plus s upon pf minus pi divided by the norm of that, the length of that, the vector, parameterized by this s. This is ps or dp upon ds is this, and d square p upon ds square is equal to 0. So, since dp upon ds is defined, you can see that the tangent vector is constant, and since d square p upon ds square is equal to 0, that means the normal vector is not defined. So, again B is not defined, the oscillating plane is not defined. Okay. Circular path, it is just a matter of what you specify. So, you can need to define unit vector for the circle axis, and then you need to define a point on the axis. That we know, to define a line we need two things, a direction and a point on the line, and then we need the position vector of at least one point on the circle, because there is an infinite number of circles which exist on this axis. So, once I specify one point, then I know that that has to be a constant radius r. So, the rest is quite simple. You can define this delta as equal to pi minus d, and once you do that, and you can show that if this point pi is not on the axis, that means not a degenerate circle which vanishes into a point, then delta transpose r is less than delta. So, then C becomes d plus delta transpose r into r. Now, r is not the radius, right, the radius is rho. R is the this direction cosine of the vector. So, then you are defining the center. Once you have defined the coordinate of the center, the rest is quite trivial, right. You can find out the radius if you want. It is just c minus pi, norm of that is the radius of circle. You can find out all other properties you are interested in this. Okay. So, this is one of the many ways of specifying a circle in space, but this is a reasonable definition, because usually you will know, okay, here is a circle, it is bent like this and there is a point on the circle, okay, where the axis is. So, then you can define the circle. Now, this is not a parametric definition of the circle. There are too many parameters, right, r, d, pi. So, the idea is that, so if I fix a coordinate frame where the z prime axis goes along this, the x prime axis goes along this, the y prime axis is trivial, right. So, in this coordinate system, the circle is very easily defined, right. It is simply rho upon cos s upon rho and rho times sine s upon rho and 0, well, s is the parameter. So, as you move, you will just keep on tracing the circle in that local coordinate system, and you start from the point pi. It's a very simple definition. We then just have to move it to the other frame. So what do? You take your vector field, you multiply it by the rotation matrix R. We are very good at writing the rotation matrix R, and you shift it by the distance which is the center of the circle. So we have this, and in which we write C in the global frame, and we say R is the rotation matrix that we know how to write. We just have to write the direction cosines of x prime, y prime, z prime, and we can get the rotation matrix. And then essentially once you have defined like this, then you define dp upon ds. So you get minus sin s upon rho cos of s upon rho, and then d square p upon ds square you get in this form. So you know all the vectors. So this gives you the general term. So now we come to planning for the position. So again we get back to the 3 into 1 vector. Now we say that the origin of the end effector frame moves from pi to pf in time tf. Okay. And then these are just formal definitions. Okay, we are going from pi to pf in the direction induced. Arc length s is equal to 0 at t is equal to 0, s is equal to sf at t is equal to tf. Okay. So all we do is we define the timing along the path by the function st, which can be a cubic polynomial or consist of linear segments with parabolic blend, so on and so forth. And then the problem is roughly solved. So once you have it, the velocity of the point Pe is P dot is s dot dP upon ds, that's equal to s dot t. Now what have I achieved here? Given the point, I can find the vector t that we have already established. So all I need to do is I need to do s dot. I have done a polynomial interpolation. I need to find s dot, and I multiply with the local vector t, and then I have the velocity. And similarly, I can find the acceleration. Okay. Now why do I need this? Because I can then very quickly write down at the joint level what is the local acceleration, what is the local velocity, the joint velocity and the joint acceleration by doing a Jacobian control or something similar to that. And I can use all these inputs, like when I did the linear interpolation or interpolation on joint axis, I said there could be so many specifications. I either say that I specify position and velocities at points, or I say I specified position and I want velocity, acceleration, continuity at each individual joint. So to deal with all of these individually, I need this data. But once I have the parametric form, I can calculate these very easily.
Sir, as s is a scalar quantity, so this means that the acceleration is always in direction of t.
Well, this is for the linear case. You look at this now. This is for rectilinear motion. If you take a circle, then you get this as the velocity, right? So this velocity is aligned with the tangent vector. If you take the acceleration, that has two terms. Okay, this is aligned with the tangent vector, and this is aligned with the normal vector. So this is sometimes called the Coriolis term. Okay. And so this is just derivation, so you can easily find out these terms and then you can map it. So finally we get to sequence of points. So you have n plus 1 points which are connected by n segments, and Then you have arc length associated with the jth segment connecting Pj minus I to Pj, and then you can essentially get this definition of the function, and now we are looking at Sj as a function of t. It is defined like this. So, for each segment until you reach Tj minus 1, Sj is 0. So, this will not contribute. So, writing the full path as a summation of large number of polynomials. Okay. Now, by making sure that the value of this Sj is 0 until it is Tj minus 1, you are making sure that this term, the jth term, does not contribute to anything else except for the small segment which is in there. And then you use the function Sj prime, which can be any polynomial between these two values, okay, and this is equal to norm of Pj minus 1 between Tj and Tf. So, if you want to, you can compute the velocity and accelerations based on this by simply taking derivatives, okay. And finally, you can blend by just changing this. Instead of going from Tj minus 1 to Tj, you just have a minus delta t where you will blend in that small area. So, this is just a small variation of it. So, then you can successfully blend it also. So, what is the essence of the lecture today? Essence of the lecture today is that if you have primitives or you want to deal directly in the operation space, you have to go through and first parameterize that space so that you can deal with it. So, using a single parameter, then you take that single parameter and did to that parameter between the parameter S between Si and Sf, and between Ti and Tf you do the single axis interpolation that we did over the last 3 lectures, and then you map this back into the joint domain, and you can do the control at that level, and if needed at the joint domain you do some micro interpolation. So, for that you still have to go back and use the joint interpolation techniques that we discussed. So, it is a 2-step process, and how often, so you can see that this is slightly more complicated mathematics than what you did in the previous class, previous lectures, all of this, and it is very easy to write d squared p upon ds squared, right, norm of that, but calculating it is slightly more difficult. So, it has to be done on every point, okay, and then your function is difficult, so you have to write expressions for that. So, there is loading, okay. So, for most mechanical systems, okay, they typically operate at something between 1 hertz to 10 hertz, typical mechanical systems. There are some things which are very quicker, much quicker if you get into MEMS or these kind of technologies. So, for example, you have mirrors which switch much faster, okay. What are mirrors that switch? You know what mirrors that switch? So, you make a call to Bombay, right? How does it get to Bombay? Fiber optic. So, how does it go to the Bombay fiber optic, not to the Kolkata fiber optic? So, when you make a phone call, it actually goes along a fiber optic cable, right, and then there is a small mirror, okay. So, if it is like this, it goes to Bombay, if it is like this, it goes to Kolkata. Now, you can understand that there are so many people trying to speak on lines and it has to instantaneously switch. Actually, it is done more complicated, all the phone calls which are going to Kolkata are bundled together into a single signal for a small time duration, and so that is then sent to Kolkata, and then in the next microsecond a packet which contains data meant for Bombay is then sent to Bombay. So, physically it is actually deflected like this. Now, those kind of mirrors, they go much faster, but for most systems that you will deal with, unless you are in that area, okay, you are dealing with 10 hertz at the most. So, this basic, going from the operational space to this is done at something like 60 hertz, and then internally you close the loop much faster to drive it in the way you want to do it. Okay, so I think we just stop here today, and okay, so have fun tomorrow. Oh, tomorrow, okay, I'll have to do the orientation. So that's actually a small lecture because you already know how to do it. You know how to do it? How do you parameterize orientation? So today I just did position, right? I'm talking about rectilinear circles, point to point interpolation. How do you handle orientation? Another parameter. What is the parameter?
Any parameter defining the three other angles at any.
Single parameter define three Euler angles is very difficult. That's why even Euler could not find it. Right? He just came up with his angles. But Casals was smarter. Remember Casals? No? Remember Casals? So we'll use Casals. Okay, and then so we parameterize it, and then we can quickly interpolate on that and get where we want to do it. So it's going to be a short lecture. We'll just go through it tomorrow. Okay.